Now we will be deriving Boyle's law. So derivation of Boyle's law is actually very simple, and we will be doing it in a very simple manner. But before we do that, let us just revisit what is Boyle's law. Boyle's law says that pressure into volume remains constant for a gas if its temperature and mass are held constant. So temperature and mass is not really changing, then pressure into volume remains constant. So that is the Boyle's law. Now here is a simple demonstration. The temperature is held constant, the the mass is held constant, and we are saying that as we decrease the volume, so volume is decreasing, the pressure is increasing, and therefore this relationship holds. PV is equal to constant. Of course, this Boyle's law only applies to certain kind of gases, and those gases are known as ideal gases. Okay. Real gases also obey the Boyle's law, but not to the complete extent. Okay, to some extent they also obey it, but ideal gases definitely obey the Boyle's law. Ideal gases are just like real gases, just like air, nitrogen, oxygen that we see around us. Ideal gases are very similar, but for doing the physics, we have made certain simplifying assumptions for these ideal gases. And what are those assumptions? The first assumption is that their particle size is very small. Okay, infinitely small. Their particle size is infinitely small. The second simplifying assumption is that there are no interparticle interactions, that the particles of the gas or the molecules of gas do not really interact with each other, they do not really collide with each other either. Now, with those two simple assumptions of the ideal gas, and given the condition of the Boyle's law, which means that the temperature is held constant, temperature is equal to is constant, and also the mass is not really changing, so it is also held constant. So those two things are kept constant. That is the assumption. We'll now do the Boyle's law derivation. So here we have a cube of side D, which we have filled with our ideal gas, which is very small small particles. Okay, so that is the thing that we are doing here. Now what about the collisions of this gas with the sides of the container? Okay, so the gas molecule came along, it hit the side of the container, and then it moved to the other side, it hit there, and then it came back and hit here. Okay, so we are only considering this face of the container, and between the two hits from this side, this gas molecule had moved a distance of 2d. Okay, and what would be the time taken to cover this distance of 2d if the gas molecule is moving with a speed of u and the time between collisions is delta t? Then it will be the distance is equal to speed into time. Okay, so that this 2d distance would be covered in u delta t amount of time. Okay, so that is the first thing that we have written. Now what about the change in momentum? Change in momentum during the one such collision. When the one collision happens, of course we know that there would be a change in momentum. The initial velocity was u and the final velocity was same. This was an ideal collision. Okay, and the particles are also very small in size, they are infinitely small in size. So this was an ideal collision. Initial velocity was plus u, the final velocity was minus u. So what is the net change in momentum? It is the mu minus of minus mu, and this comes out to be 2mu. So that was the change in momentum. Now what about the rate of change of momentum? D delta p by delta t. That is the rate of change of momentum. What about that? It is 2mu divided by delta t. Now from this equation, we can say that our delta t is equal to 2d by u. So this comes out to be 2mu squared divided by 2d. This 2 and 2 would cancel. So this delta p by delta t is nothing but force is equal to rate of change of momentum. So this is the force. This is the average force applied by the particle of the gas on the face of this container, and that force is actually equal to mu squared divided by d. That is the force. Now what about pressure? Pressure is nothing but force per unit area, so I divided by area. What is the area of this side? D into d, of course, because it's a square faced, so this will be d squared. So this comes out to be p mu squared, okay, P is equal to mu squared divided by d into d is d cube. That is of course the volume of the container. In other words, PV, pressure into volume, is equal to mass, okay, that is the mass of the molecules, which does not really change, and u squared, velocity squared, okay, or the speed squared, and the speed of the container is also not changing. Speed of the molecules is also not changing. And why is it not changing? Because we are not changing the temperature, and that is our assumption. That is our assumption that we did here, that the temperature is remaining constant, and with the temperature remaining constant, the U does not really change. So we are saying that PV is equal to mu squared. M does not really change, U does not really change because temperature is kept constant, which means that PV is equal to a constant. It is equal to a constant K, and this proves our Boyle's law. Okay, so this derivation, although it might not be asked in the exam, but it tells you several things. What is ideal gas assumption? What about the things on which the this particular PV depends? How do we make an assumption that the temperature does not really change? Why is it important? Okay, so if you remember these derivations, then you will not be forgetting the assumptions required for the Boyle's law to actually hold, and that will reduce the number of mistakes that you will do in your actual examination. Thank you.